We're demonstrating a pitch pipe organ with an H-bridge controlled DC gear motor and an NVE Smart Angle Sensor providing the rotation feedback. The motion is fast and precise despite the motor's rotational inertia. So we can have a brisk tempo. The motor driver is an isolated full H-bridge. NVE DC to DC converters power the high side, and NVE isolators isolate the H-bridge and drive the MOSFETs. Here's a closer look at the angle sensor. A magnet is glued to the pitch pipe, and the ASR012 detects the rotating magnetic field. The sensor is non-contact and can be up to 7 millimeters away from an inexpensive ferrite magnet, so there's a lot of mechanical latitude. We have a free web app to check the magnet spacing. There are 13 pitch pipe notes, so the notes are about 28 degrees apart. Pitch pipes come in various keys. We chose a C2C variant to match a C2C piano keyboard. In other demos, we use a simple single MOSFET motor drive, but you can't reverse the motor and you can't short the motor to drain the back EMF. Adding a second MOSFET to form a half bridge allows the load to be shorted. This requires a P-channel MOSFET, which are less common, and for this circuit the motor voltage must be the same as the logic voltage, which may be impractical. We can add level shifting with an isolator and a DC to DC converter. That allows different load, logic, and gate voltages. The ultimate motor drive circuit is an isolated full H-bridge, which allows us to reverse the motor, short the motor for faster stopping, or pulse width modulate to control the motor voltage. This is the detailed reference design we used for this demo. The H-bridge uses 3 isolators for 4 isolation channels. The isolation allows us to float the high side MOSFETs and level shift the low side MOSFETs from 3 or 5 volts to 6 volts. The isolators have low impedance outputs to directly drive MOSFETs, so there are no MOSFET drivers. The isolator inputs on each side of the H-bridge are connected in series, which guarantees 2 MOSFETs on the same side won't be on at the same time. A low turns on the low side MOSFETs, a high signal drives the high side MOSFETs. Tri-state turns off both the high side and low side MOSFETs. The isolators have best-in-class common mode transient immunity, which allows fast switching for high efficiency. The DC to DC converters have a full 2.5 kilovolts RMS of isolation and are the smallest devices of their type. Here's the rest of the wiring diagram. An Arduino controls the system. The speed of the angle sensor allows us to move the motor very quickly. The Arduino also connects to an air valve, keyboard, mode switch, and LED array. Gear motors typically have a lot of inertia. We ran a test of the H-bridge and motor for reversing and stopping the motor. Here we pulse the motor and let it coast by turning off all the MOSFETs. As you can see, with a 20 millisecond pulse, the motor coasts for 250 milliseconds. With the H-bridge, we can short the back EMF by turning on the low side MOSFETs. Then it only takes about 60 milliseconds to stop. Here's the procedure to read the angle, which is pretty simple. We have a proportional control of the motor pulse width. Here are the key components used for this demo. Key ILDC series DC to DC converter specifications are a DFN6 version that's the world's smallest isolated DC to DC converter. Various output voltages. We use the 6-volt version in this demo. Soft start, so the controller can start before the high side is energized. Fully isolated, and the full industrial temperature range. The IL600 series isolators have ultra-high CMTI, extended 3 to 6.6 volt power supply range for direct drive of 6 volt MOSFET gates, full isolation, no input side power supply, and ultra-miniature packages. Finally, the ASR angle sensor specifications include 0.1 degree precision, wide field operating range, high speed, and ultra-miniature. Visit our website or email us for more information about our DC to DC converters, isolators, or sensors.